Okay, so in each of these circumstances, what we've been looking at is we've been looking at the speed at which the train is moving up the hill. And that's, in this metaphor, it's analogous to delta N over N delta T, the per capita population growth rate. Very often, though, what biologists are interested in is not, the perspective of the individual in the population, but, how fast is this population growing? Is it going to add 100 new individuals by next year? Is it going to add 1,000 new individuals by next year? Is it going to shrink by 500? What we need to do to kind of grok that, to understand that in the context of this train metaphor, is to introduce kind of a different way of thinking about it. When you've only got one train car, or one car attached to the locomotive, the train is moving very, very rapidly. But if you were trying to get freight delivered, if you were, a train company trying to deliver freight, this is not how you would do it. Because dragging one car at a time is really pretty slow. So we multiply both sides by n. Now we're back to this form of the equation. Delta n over delta t equals R max times this term times n. And now what's over here on the left side is the population growth rate, the speed at which the entire population grows. And what we're going to be thinking about in terms of the train is the rate at which freight gets delivered. So when the train is moving very fast, but it has this tiny little load of cargo, it's actually not delivering the cargo all that quickly. Let's take a look at how this plays out. We're going to plug in some numbers here again. K is going to be 10 train cars. The locomotive can go at some maximum pace of R max, and it has some certain number of train cars trailing behind it. Okay, so when n is almost 0, again, train's moving very fast, but there's only one train car. So in this case, the speed of the train is 90% of its maximum. It's carrying one train car, and so the rate at which it is delivering freight is 0.9 times R max. If you add on a couple of more train cars, the train goes slower, but at the same time, it's dragging more freight. And so actually, even though it's running only at 70% of its maximum speed, because you're delivering 3 train cars at a time, the rate at which it delivers freight goes up to 2.1 times R max. When n is half of k, you've got 5 train cars. Okay, now it's only running at half speed, but it's delivering a lot of freight, so you're up to 2.5 times R max. You might be tempted, if you were trying to deliver freight at, as quickly as possible, to keep throwing on train cars. But something interesting happens once you pass this halfway point. Yes, in this case, the train is delivering 8 carloads of freight at once, and that's a lot, but it's running so slowly that instead of getting 2.5 times R max, it's only delivering freight at a rate of 1.6 times R max. So it's less effective now than it was when n was only half of k. And obviously, if you keep adding cars onto this train, you're going to hit some point where, great, it's got 10 cars attached to it, but they're not going anywhere. And so the rate at which you're delivering freight is 0. Okay? So 2 basic lessons here. One of them is, really pretty obvious. As you add cars to the locomotive, its ability to move up the hill, its speed at which it moves up the hill, goes down. Okay, so as a population grows, each individual's ability to survive and reproduce goes down. Because remember, that's what the speed at which the train moves is equal to. It's delta n over n sub delta t. That's the births minus deaths on a per capita basis. It's more complicated when you consider how rapidly the train is delivering freight. Okay, at first, when you have very few cars, the train is moving fast, but it's not delivering much freight with each run. And so your freight delivery rate is really pretty low. As you add on more cars, that increases because you get more freight delivered with each run, even though the train is slowing down. You hit a maximum rate of freight delivery right around here, where N is about half of K. And past that point, the freight delivery starts slowing down and down and down. Whether you're talking about how rapidly the individual train is moving or whether you're talking about how rapidly it delivers freight, when N is equal to K, the train stops. Okay, its growth, the population growth, whether you're talking about per capita or the whole population, that growth drops to 0. So recap here, when you've got a population size that is near to 0, speed's very fast, but you don't have many train cars, you don't have many individuals reproducing. And so the fact that they're reproducing, they're having a lot of offspring each, still it doesn't amount to very much. Population growth is still very slow. When you have a population size that is, reasonably small, each individual is reproducing pretty rapidly. Not the highest possible rate, but still pretty rapidly. And there are more individuals than there were here, and so you're cranking out more offspring than you were before, but really population growth is, it's kind of middling here. When you get to half of K, there are a considerable number of individuals in a population. And even though their ability to reproduce and survive is really only about half of what you'd see when a population really starts getting going, this is the time, this is the point in population growth when the population is growing most quickly. If the population continues to grow, obviously you've got more individuals reproducing, but each one is barely able to squeeze out one or a few extra offspring. And so population growth as a whole slows to moderate. As you're approaching the carrying capacity, as the population approaches the carrying capacity, lots of individuals reproducing, but they're all barely able to replace themselves. You're getting very slow population growth. And when you get to K, when each individual is only able to replace itself, it really doesn't matter how many individuals you have present, because the population is not going to grow anymore, because each individual can only replace itself before it dies. Okay, this equation that we've just been dealing with is what's called the logistic growth equation. And if you're looking at population size over here on the vertical axis as a function of time here on the horizontal axis, what you see is this what's called a sigmoid curve. That means it's S-shaped. At first, it looks like exponential growth because the rate at which the population grows actually accelerates over time. But that acceleration slows. Real exponential growth would go up like this until it becomes practically vertical. But what happens with logistic growth is acceleration slows until finally you start getting deceleration as this population grows even further. And as the population size approaches this constant K, the carrying capacity, growth gets slower and slower and slower. The population only approaches K, never quite reaches it, and population growth basically becomes 0. And the population stays at size K, at size N equals K, until something else happens. Does this happen in the real world? Yeah, it does. This is the historical data, actually, for the sheep on Tasmania. And you can see there's a lot of noise here. Some years the population goes up, some years it goes way down. But over the long term, it does a pretty good job of tracking this solid line. And the solid line is a logistic population growth equation. Okay, and this pattern is seen as all sorts of individuals, of all sorts of species. You get accelerating growth at first, then it slows down, and eventually levels off at some maximum. beyond which, the population seems to fluctuate, but it never seems to get way up above that level. So in a nutshell, here are the two equations that you need to know. The exponential equation and the logistic equation. These are the shapes they take on, with the exponential equation, the exponential growth always curving upward, always steeper. The logistic growth accelerates upward and then comes back downward. You'll sometimes see these equations go by slightly different names. This is called the density-independent growth equation. One name for the variable n is population size, as I've told you, but it's also sometimes referred to as population density, the number of individuals per unit area. This equation reflects density-independent growth because the rate at which each individual reproduces has nothing to do with the population size. So each individual is able to crank out the same number of babies over its lifespan, whether the population is very small or very large. Okay, and you can see that, by the way, if you take this equation and divide both sides by n here, you get delta n over n delta t is just a constant. It's R max, and R max stays the same no matter what n is. Over here, you have population growth, particularly the number of individual offspring that an individual is likely to have over its life. And that really depends on the population density. So this is called density-dependent growth. The number of individuals that, or the number of offspring that an individual can expect to have during its lifetime depends on density. Biologically, here's the difference between the two. Populations will grow exponentially. They will experience what's called density-independent growth only when competition isn't really having an impact at all. When competition starts to affect individual survival or their reproduction or both, then what you're going to see is something much closer to logistic growth, because the rate at which individuals are able to more than replace themselves will really start to depend on population density.